So, how often do you actually think about the microscopic math that keeps high-speed machinery from just, vibrating itself to pieces?
Honestly, it's probably not something most people think about at all.
Right. But welcome to today's deep dive, where we are unpacking exactly that. We're looking at a highly specialized technical briefing on mechanical vocabulary for precision transmissions,
Mm.
specifically harmonic reducers.
Yeah, our goal today is to decode the exact terminology that R&D and manufacturing engineers use to communicate these really complex physical limits.
Because in the world of high-level engineering, precise language isn't just about communication, is it?
Oh, absolutely not. I mean, it literally dictates how these incredibly compact systems actually survive physical stresses.
Wow.
Yeah, a single misinterpretation of a term on the manufacturing floor translates directly to catastrophic failure.
Okay, let's unpack this. We begin at the very center of the system, right? The wave generator. With the core shape isn't a simple circle, it's an elliptical cam profile.
Exactly. It's a precision curve, and it dictates how the flex spline deforms and meshes, and it has to be ground with perfect symmetry.
Because if the symmetry of that curve is off by even a micron, you aren't just losing mechanical efficiency at high rotational speeds, you're creating unbalanced radial forces, which I imagine will literally shake the entire joint apart.
Oh yeah, that uneven load distribution is just an absolute killer for high-speed machinery. So to keep that elliptical shape spinning correctly without self-destructing, engineers have to fiercely control what's called concentricity tolerance.
Okay, concentricity tolerance, meaning the wave generator's hub bore perfectly aligns with the outer diameter center.
You got it.
I always compare this to like driving a car with a slightly misaligned wheel rim. If that tolerance is off, you no longer have a uniform, even gap between the gears as they mesh.
Right, and that wobble creates an angular deviation, which, generates excessive friction and heat.
And heat is the ultimate enemy here.
100%. But concentricity is really only half the battle. Let's say the overall shape is perfectly aligned, but the microscopic spacing of the individual teeth is off by just a fraction of a millimeter.
Then you hit the parameter called pitch error, right?
Yes, exactly. Pitch error is the deviation between the theoretical and the actual distance of adjacent teeth on the circular spline.
And excessive pitch error ruins the system because it causes periodic velocity fluctuations at the output shaft.
Right. So if the teeth aren't spaced perfectly, the gears aren't meshing smoothly. They essentially catch and release.
Wait, really? So it literally creates this microscopic stuttering.
Exactly. And that stuttering travels all the way down, say, a robotic arm, completely ruining the precision of the entire machine.
Here's where it gets really interesting to me, though. Even with perfect spacing, how do the teeth survive the physical friction without just wearing down immediately?
Well, that comes down to surface hardness. To resist wear and pitting, the circular splines undergo treatments like nitriding or induction hardening.
And the goal there is to elevate the hardness specifically to HRC 50 to 55 on the Rockwell scale, so they can withstand that incredibly high contact stress.
Right, and with nitriding, you're literally infusing nitrogen into the surface of the steel.
It creates this armored shell on the outside of the teeth while keeping the inner core of the metal somewhat flexible, right?
Which is the critical part. If the entire gear was hardened completely through to that HRC 50 to 55 level, the steel would become way too brittle.
Oh, so it would just shatter under a heavy load.
Exactly. You need that exact balance. A tough exterior to resist wear, and a ductile interior to absorb the shock of constant high-speed meshing.
But designing that perfectly armored, intricately spaced gear on a computer is one thing. Actually carving it out of hardened steel in a compact space is another.
Yeah, the manufacturing reality is wild. What's fascinating here is the physical limit called tool interference.
Because these harmonic reducers are just so incredibly compact.
Right. When engineers are programming the gear shaping process, they have to mathematically verify that the cutting tool won't accidentally crash into the non-machine parts.
Since the clearance between the cutting head and the hub wall might be almost non-existent.
Yeah, the software has to map the tool's path with absolute certainty. It's constantly checking for interference to ensure the cutter can safely reach the full tooth depth. You're basically trying to carve microscopic perfection into hardened steel inside a deeply confined metal pocket.
So what does this all mean for you listening? I think understanding this exact phrasing shows how high-level engineering relies on precise language.
Definitely. Words have physical weight here.
Right. A single misunderstood term like pitch error or concentricity translates directly to catastrophic physical failure on the manufacturing floor.
Yeah, every specification acts as a safeguard.
Exactly. So the next time you watch a robotic arm move with liquid smoothness, ask yourself, just how many unseen elliptical calculations, tool clearance checks, and microscopic hardening processes were required to make that single simple motion possible?